Eigenvalues and eigenvectors play a central role in linear algebra and differential equations. In the next few minutes, we'll talk a little bit about what eigenvalues and eigenvectors are in terms of their definitions and also graphically, and then we'll do a simple calculation. So let's take a simple 2 by 2 matrix, 5, -6, 3, -4, and let's assume that V is some vector in R2. We want to know something about the vector A times V. This matrix A times a vector V will again be a vector in R2. Well, in general, we don't really know. All sorts of things could happen. A could take the vector V, it could stretch it, it could rotate it could reflect it about an axis, it could shear it could do all sorts of things. But let's take a look at a particular example where the vector V in question is the special vector 2, 1. What does A times V look like? Which I'll plot down here. So if we choose the particular vector, 2, 1, and multiply it by A on the left, we have 5 times 2, which is 10, minus 6, which is 4, 3 times 2, which is 6, minus 4, which is 2. We get the vector 4, 2. But that's merely twice V. This particular vector V is special. I chose it to be special insofar as multiplying it by A merely stretches the vector by a factor of 2. So the output would look something like this. All we've done is we've taken the vector V and we've stretched it by a factor of 2. So that's really what an eigenvector is. And suppose that A is a square matrix. If V is a non-zero vector, non-zero, that's very important, and if A times V is lambda times V, where lambda is a real number, we say that V is an eigenvector of A with corresponding eigenvalue lambda. So we're simply stating that multiplying this special vector V by the matrix A merely stretches the vector V where the multiplying factor is the eigenvalue of lambda. Now, where does eigen come from? It's eigen, not eigen. Eigen is German and it translates roughly as distinctive or idiosyncratic. In the example above, 2, 1 is an eigenvector of A with corresponding eigenvalue lambda equals 2. So how do we calculate these eigenvectors and eigenvalues? So in general, if A is an n by n matrix, it will have n eigenvector-eigenvalue pairs, although some eigenvalues may be repeated and some might be complex. So let's think about the definition of eigenvector and see if it can help us determine how we calculate these eigenvectors and eigenvalues. Now remember, if V is an eigenvector, then V is not the zero vector. So by the definition, that means that A times V equals lambda times V for some scalar lambda. Now I'm going to do a little algebra calculation in a moment, and it's going to help me to insert an identity matrix here. The identity matrix times V is still V. You'll see why in just a second. So let's rearrange the quantities. A times V is lambda times the identity matrix times V. We essentially got that from the definition of eigenvector-eigenvalue. That means that if we subtract lambda times the identity times V, we get the zero vector. Not zero, a number, but the zero vector. And you look at this and you can see how we can factor the vector V out on the right. So we get A minus lambda times the identity times the vector V, which is our eigenvector, that's what we're trying to determine, equals the zero vector. In other words, we have that. Now, remember V is not the zero vector. Whenever we have the matrix vector equation, B times V equals 0, this is what we call a homogeneous system of equations. Whenever it has a solution that is not the zero vector, in other words, the solution is non-trivial, we know that the determinant of B is 0. This is really a result of what's known as the invertible matrix theorem. That means that in order for this to have a non-trivial solution, V is not the zero vector, the determinant of A minus lambda times the identity has to be 0. So what we do is we take that equation and we solve it for lambda. And that's how we find the eigenvalues. We find the eigenvalues first, and then we can go and we can determine the eigenvectors. So let's do a simple calculation. Let's take a look where A is the matrix 5, negative 6, 3, negative 4, which we were looking at a moment ago. So we take A times A minus lambda times the identity. Lambda times the identity would just be placing lambdas on the diagonal of the identity matrix. So we get 5 minus lambda minus 6, 3 and minus 4 minus lambda. And we want to compute the determinant of that. So we multiply 5 minus lambda times minus 4 minus lambda, and then we subtract 3 times negative 6. Now here's one hitch. If our matrix A had been 3 by 3, the determinant calculation would be more involved. We might have to use cofactor expansion. If we simplify this, we get lambda squared minus lambda minus 2, and we want to determine when that is equal to 0. This factors easily. So the eigenvalues are lambda equals 2 and lambda equals negative 1. Now let's focus on the first eigenvalue, lambda equals 2. Now we know from a few minutes ago that A minus lambda times the vector V has to be the zero vector. This is a system of equations which we can write using an augmented matrix. We can take an augmented matrix, put the zero vector in the rightmost column, and put A minus lambda times the identity over here, and we can solve it, and that's going to give us our eigenvector. So when lambda is 2, I substitute 2 in, and I get 5 minus 2 minus 6, 3 minus 4 minus 2. Simplifies to be that. We can take this system of equations, we can row reduce, and we get 1 minus 2, 0, 0, 0, 0. This is a system of equations with infinitely many solutions. That will always be the case when you calculate an eigenvector from an eigenvalue. If not, that means you've made a mistake. So V1, which is the first component of the vector V, this is a scalar, is a pivot column. This is not. So that means that V2 is going to be 3. I might as well set it to be 1. That's nice and simple. V1 would be minus 2. V1 would be 2V2, which then would be 2. So that means our first eigenvector is 2, 1. V1 and V2 were just the components of the vector V1 and V2. Of the vector V1. You can show using a similar process, and you can check this on your own, that if lambda is equal to minus 1, then the vector V2 is equal to 1, 1. So that's a simple example of how we compute eigenvalues and eigenvectors and what they mean graphically in the two-dimensional case.